Excellent. So welcome everyone to today's Astroparticle seminar. We're happy to have as our speaker Ali Kheirandish from Penn State. Ali got his PhD at the University of Wisconsin-Madison. Then he was a postdoc at Wisconsin-Madison as well. And then he moved on to his current postdoc position at Penn State. He has, for several years, worked on different aspects of high-energy neutrino physics and astrophysics, both as a member of the IceCube collaboration, but also as an independent theorist. He has worked on things ranging on a number of different topics, from neutrino attenuation inside the Earth, in direct search for dark matter using high-energy neutrinos. And for that, he is a co-author of a state-of-the-art code to compute the neutrino flux from WIMPs, the scatter and high-energy neutrinos of the galactic dark matter, and also on the astrophysics side, high-energy neutrinos from FRBs, the searches for galactic sources of high-energy neutrinos, connections between gamma ray and neutrino emission, including from radio galaxies and blares of flares. And today, he's going to talk to us about prospective sources of high-energy cosmic neutrinos. So Ali, please take it away.
Great. Thank you, Mauricio, and thank you all for the invitation and the opportunity to talk about prospective and potential sources of high-energy cosmic neutrinos. The neutrino sky or the universe neutrino has a spectrum that spans about 20 orders of magnitude in energy. At the lowest energies, we have the relic neutrinos from the early stages of the universe, cosmic neutrino background. And as we progress towards higher energies, we have the solar neutrinos starting at few keV energies and higher. And then we have the supernova 1987, the first astrophysical signal of neutrinos beyond the solar system appearing. And at a lower level, we have the diffuse supernova background that is coming from all the supernovae that produce neutrinos at MeV energies through the universe. Then at the higher energy, we have atmospheric neutrinos, astrophysical neutrinos would kick in and become dominant component after 100 TeV energies, which could be produced in sources like active galactic nuclei or gamma ray burst. And at the highest energy, we have the GZK flux. So the subject of this talk mainly focuses on the high energy part of this spectrum, energies above GeV and TeVs. And for us, the background is the atmospheric neutrinos, which are produced in the cosmic rays, very high energy cosmic rays interacting in the atmosphere, producing charge and neutral mesons that would promptly decay to charged particles and neutrinos, which would arrive at your detector and act as the background for the astrophysical ones that we're looking for. In the astrophysical beam dumps, we have cosmic rays interacting with the ambient target material or radiation, producing again charged meson, which will decay to neutrinos, and those arrive at the Earth. And the highest energies, at energies of 10 to the 18 and above, we have the GZK neutrino that are produced in the interaction of ultra high energy cosmic rays with the cosmic microwave background. So the idea of neutrino astronomy emerged early in the field, soon after the discovery of neutrinos, as neutrinos present the ideal cosmic messenger to do astronomy. As I mentioned in the previous slide, accelerated cosmic rays interact with gas or radiation in their environment, which provides the beam dump, and then production of pions would result in production of neutrinos and high energy gamma rays that should accompany the high energy neutrinos. But neutrinos are hardly interacting, which basically enables them to evade any absorption that can block them from arriving at the Earth, so they are not absorbed. They are neutral, so they don't get bent in the magnetic field. They can arrive directly from the source, and they can point back to the origin of cosmic rays because you need accelerated cosmic rays for their production. And they become the exclusive messengers in the range of like 10 TeVs and higher, since the photons are absorbed and cascade down when they travel toward the Earth. So they present an ideal cosmic messenger for doing astronomy. However, the flux is very low, as we see in the spectrum slide. And in order to see them, we need immense detectors, very large detectors that increase the chance of observation for them. And that was realized by the construction of the IceCube Neutrino Observatory, the first cubic kilometer neutrino telescope that is currently operational. So IceCube is located at the geographic South Pole. It is constituted of more than 5,000 digital optical modules like these that are buried more than a kilometer below the surface of the ice. There is the array has 86 strings, and it can detect neutrinos with energies higher than 100 GeV each. And there is a more dense array inside called the core, which can reduce the threshold to few GeVs for us, and which can enable us to study either sources at lower energies, or do a study of atmospheric neutrinos for oscillations and other stuff. That NBIA is actually a core member of this kind of projects. So the detection principle in IceCube is basically built upon identification and detection of the chunk of light that charged particles produce in the interaction of neutrinos produced in the transparent media of the ice. So charged particles traveling faster than the speed of light emit chunk of light, and the digital optical modules that are buried in the ice can detect them. And the intensity of the light and the timing can be used to reconstruct the direction and energy of the neutrino that has induced the charge current, that induced by the charged particles. So we have three main morphologies for the events that we see in IceCube. First is the charged current muon neutrino interaction that produces a track. Here you see an upgoing track, and the color goes from early to late here. And tracks have do not have like the best energy resolution, but they have particularly good angular resolution, less than a degree in general, and better than 0.5 degrees at high energies, which makes them suitable for astronomy. Then we have neutral current interaction of any flavor of neutrinos, and the charge current interaction of other neutrinos other than muon neutrino, which will produce a blob of light inside the detector that almost propagates isotropically, creating a sphere of light. And these are cascades or showers in the detector. They have relatively good energy resolution, because if they are contained in the detector, you can count all the deposited energy to the detector. However, because you don't have a elongated track-like path of light, you cannot reconstruct the direction as good as the muons that pass through the detector. And their angular resolution is orders of 10 degrees. Another nice feature so far haven't observed is like a double cascade or double bang that we have, that if you have a charge current new tau interacting, creating a tau, the tau decays and creates another blob of light. So you have two cluster of light in the detector, and that is produced by very high energy new taus interacting in the ice and passing through the detector. So among these three morphologies, the cascade isolated cascade analysis was the first to show us the high energy neutrino flux. Here, this is the current status of the high energy neutrino spectrum measured by the IceCube, and at higher energy from other neutrino detectors. So at the lowest part, we have the atmospheric neutrinos from muon neutrino and electron neutrinos in the atmosphere, and they drop very fastly as they reach to higher energies. And we also have the prompt component that is have not been seen so far, but from the charm meson decay in the atmosphere. And the first channel that observed high energy cosmic neutrino flux was the high energy starting events, which utilized a veto to reject the background and select events that are contained inside the detector. And 7.5 years of observation yields a significance better than 8 sigma with 100 events, all flavored, with a spectrum, a simple parallel spectrum that goes to e to power minus 2.89, quite a soft spectrum between like 60 TeV to few PeVs. Then another channel confirmed the observation after a few years of observation, confirmed the existence of the extraterrestrial flux of cosmic neutrinos, and that channel was the true going or upgoing muon tracks. More than 8 years of observation is available now. Around 7 sigma is the rejection of the flux being from atmospheric origin, and there are more than 500 astrophysical neutrinos. However, a lot of them are buried below the background at lower energies, and at highest energies we have similar number of like events with high probability of being astrophysical in the sample. And the flux is slightly harder. It's around minus 2.3, and it spans a higher energy range. And there are a couple of points about this spectrum. The fluxes are compatible in the common energy range. The level is the same. However, the feature that we see, the harder slope at higher energies, the softer slope at lower energies, and the medium energy excess that appears at around 30 TeV, it can hint towards different sources being responsible for the production of cosmic neutrinos, which is one of the things I'm going to refer to as we progress through the talk. And at the higher energy part of this spectrum, we have the current limits on the cosmogenic neutrino flux, the GZK flux, that we have not seen so far, and is the subject for the search of future neutrino telescopes as well. So this is what IceCube sees when we look at the whole energy range and when we look at all the events that we see. So we cannot find any signature of anisotropy in this plot. And remember that I have not included the angular uncertainty of events here. So this is 1 year of IceCube, more than 130,000 events here, and everything looks quite isotropic here. If we look at the high energy, the highest energy events, you can see that like this, there are around 100 events here, and you can see that almost none of them are on top of each other, and their clustering is not happening. And the fact that the distribution is quite isotropic means that the flux is coming from extragalactic sources, which puts a constraint on the galactic component of the dark matter. The idea is to look for the source of these neutrinos, and different techniques have been implemented to do so. And today I'm going to first talk about what possible sources are and what we have seen so far. So any source that is responsible for the production of TeV to few PeV cosmic neutrino flux that we see should have two main property. First, it should be able to accelerate cosmic rays to energies beyond PeV, which means that they should produce high energy, very high energy, and ultra high energy cosmic rays. And then, similar to the accelerators and the beam dumps that we have on Earth, you need an accelerator here. Then it has to enter a beam dump, which could be provided by the radiation or the dust or material, the gas that is surrounding the source. And that beam dump should have enough density that induces pion production and then neutrinos. And there are sources that have been historically identified as potential sources of cosmic rays and neutrinos. Among them, this is not an exhaustive list, but among them are the supernova remnants that have been suggested early in the field as the potential producers of cosmic rays and neutrinos, gamma ray bursts that are gigantic explosions of light, and the active galactic nuclei with a black hole at the center, an accretion disk around it, and jets coming out of it that have been seen in very high energy gamma rays. So these are potential sources, and when we think of this kind of production, we have the protons again hitting, for instance, gamma rays, producing pions, which will decay to gamma rays and neutrinos. Gamma rays would cascade down, but the neutrinos can arrive at Earth at the same energy. And the production is basically governed by the threshold that is put by the kinematics, and the maximum energy of the gamma rays that we expect on Earth depends on how much cascade the gamma rays face, and that is determined by the limit that the threshold that they meet for production of the pairs. And the production rate of neutrinos and gamma rays can be simply connected to each other when there is no absorption, and it basically depends on the energy relation and the number of pions that is produced in the initial interaction, either it's photohadronic or hadronuclear interaction. Cascading inside the source, and as the gamma rays travel toward the Earth, can change this relation and reduce the flux of the gamma rays that we might see at the same energy on Earth. So in this talk, I first will start talking about the recent developments that we had in the identification of source of cosmic neutrino flux. Then I will talk about three prospective sources of cosmic neutrinos. I will talk about the neutrino production in the corona of active galactic nuclei. Then I will spend some time talking about the searches that we have done in order to identify the galactic source of high energy neutrinos. And finally, I will talk about the expectation for observation of high energy cosmic neutrinos from core collapse supernova. So let's start with the developments and the progress that has been made after almost a decade of IceCube's observation. So when we talk about searching for the source of neutrinos, we usually do we usually utilize different techniques. So we either look for the clustering of the events, which is an untriggered search in a space and maybe time, to see if the events are autocorrelating, if we do see a cluster of events in some direction in the sky. Since we don't have a priori knowledge whether or not there is a source there, we do a scan, and that scan results in the trials that should be accounted when we are searching for the excess. Another type of search is the source search, when we have pre-identified regions of interest in the sky, and we search for the correlation of the events and presence of any excess towards them. So that's the source search, your source list search, as you may see in IceCube publications. And another type of search that is commonly used is the stacking search, when we search for collective neutrino emission from a catalog or class of sources, and we can test hypotheses like if the high energy neutrino emission is correlated with any kind of multi-wavelength emission, electromagnetic emission from a source, for instance. And then for this purpose, we add the signal on top, from different sources on top of each other, and we test a cumulative neutrino emission from all of them. On top of this, we have the real-time analysis when we see a high energy neutrino and follow up on this, and we have the neutrino alerts that we issue, and the telescopes follow up on this, which empower these the neutrino searchers by identifying the most probable locations that we should be expecting neutrinos from. So this is the neutrino sky after 10 years of IceCube's 10-year point source analysis. So the sky map you see here in equatorial coordinates is showing the local p-values for each point on this sky. So you have the northern sky hotspot identified here, and you see the southern sky hotspot here. And the northern hotspot here is the zoomed version. It actually coincides with a very interesting source named NGC 1068. And as I said, this is an outcome of the an untriggered search. So this is a search for excess all over the sky. So there's a scan. So you have to count for the trial for the number of locations that you have looked at. But although like for about 10 years, nothing has survived the trials, today we are seeing that this excess over the source can pass the usual significance level and reach to about 2.9 sigma, which is almost 3 sigma, which indicates that the anisotropies are emerging in the data. So here on the left, you can see the sensitivity of the 10-year analysis to e to power minus 2 and e to power minus 3 spectrum. And the triangles that you see here are the sources that are incorporated in 10-year analysis. And in here, you can see that a lot of sources emerge above the sensitivity line between the sensitivity and discovery potential, and few are actually matching the discovery potential. So if you hadn't have the trials that you have to account here, you would have had events with significance that surpass 3 sigma. So the most significant sources, the 4 that have p-values smaller than 1%, are NGC 1068, which is actually the hottest spot in the source list and the all sky scan, and 3 other blazars, TX05056, that you probably have heard of about, and 2 other blazars here that I have singled out. And overall, the when you do the population study, when you like test how likely is to find anisotropy at this level, when you have a list of 100 sources pre-selected, and you do this, and how likely is to get this excesses, you find that in overall, you can reject isotopic distribution of the events by 3.3 sigma, which is one of the main outcomes of 10-year analysis of the IceCube. So I first should talk about the TXS0506 in those between those 4 sources, and then I will come back to the hottest source, NGC 1068. So TXS0506 plus 056 was a blazar that was identified in a multi-messenger campaign, and it presented the first coincidence, and there were more news about it when we looked at the archival data. So in a multi-messenger campaign, after IceCube saw a 300 TeV neutrino on September 22nd, 2017, like about a week ago, it was its 3rd year anniversary actually. So 4th year anniversary, sorry. So IceCube saw a very high energy neutrino. As I said, IceCube issues alerts, and the event was followed up by different telescopes. And in one of these follow-ups, Fermi Gamma Ray Telescope identified enhanced emission from this source. And then MAGIC also saw a high energy emission from the source, which hinted at the very high energy gamma ray emission and for potentially cosmic ray from this source. And the chance of coincidence was found better than 3 sigma for this source. So this was the first identification and coincidence that surpassed the evidence level significance and presented the first identified potential identified source of cosmic neutrinos. So the source was an intermediate synchrotron BLAC located at a distance of around 3 gigaparsec. It is among the 50 brightest blazars, and it actually outshines the nearby sources like Markarian that we see. And in fact, it was one of the preeminent sources in the A-grade flux, like before Fermi era. And when IceCube looked into the archival data, it was identified that there is a neutrino flare in the period of 2014-15 with more number of events than the alert that we had in the 2017, which was quite surprising and added to the interest here. And this was also found at the level of 3 sigma. So but it came a very big surprise. There was no gamma ray enhancement during the emission. So in summary about TXS, there were 2 independent analyses that provided compelling evidence for neutrino emission from TXS. But when you look at the 10-year, almost 10-year period of the neutrino emission from TXS, as it appears in the 10-year analysis of IceCube, the flux is dominated by the 2014 neutrino burst. And contrary to the one that have been seen coincident with the alert, the neutrinos in 2014 do not come with an enhanced gamma ray activity, although there is a hint of hardening of the spectrum for the gamma rays, but it's not significant. This makes, even for 2017 neutrino event, the one-zone modeling of the blazar neutrino emission mostly underpredict the number of events, and you would rely on like something like Eddington bias, so an overfluctuation of the flux to see that event. And when it comes to the 2014 event, it becomes challenging to describe the high energy neutrino flux that has been seen in that period. It is easier to describe it by a stationary target photons rather than like acceleration in the blob of the jet. You can make a consistent production if you assume that the source is opaque to very high energy gamma rays and everything should cascade down as they exit the source. But then you need to work out the multi-wavelength and potentially most of the emission should be dumped into the MEV range that we don't have any information about at this point. And then things got both complicated and more interesting when the enhanced radio emission from TXS was observed in both periods of neutrino emission. And potential jet structure suggested a more complicated picture, which with identification of more sources that have similar trend, but unfortunately not as significant as TXS, the picture is not very clear, and we need more data, more coincidences, and more identifications to resolve what exactly is the mechanism that is producing these neutrinos in similar sources. Okay, TXS, I'm not going to go further into TXS. It requires a whole separate talk to discuss different models, scenarios, and the expectations. And from now, I'm going back to the hottest source on the list, which is coincident with the hottest spot in the all-sky search. So the source, as I mentioned, is NGC 1068. And the source is, the hottest spot in all-sky scan, and also the hottest source in the list of 100 sources that are compiled based on the high energy gamma ray emission. And it has a pre-trial p-value of around 2 × 10⁻⁹, which accounts for 2.9 sigma post-trial, like marginal to the 3 sigma that we need for evidence. Quite compelling and intriguing. So NGC 1068 and its neutrino signal deserve more detailed discussion here. NGC 1068, which is known also as M77, is a Cipher 2 galaxy with a heavily obscured nucleus. It's one of the best studied AGN. It actually played a very major role in the AGN unification scheme that we have today. And it has a complex environment as a score that has a density of around 10 to the 25 centimeter per centimeter squared, which is like quite big. And it is bright in X-ray. It has high infrared luminosity, which indicates a high level of star formation, which had made this source historically interesting for cosmic ray studies, and it's a promising cosmic ray accelerator. And the IceCube 10-year analysis, the time-integrated analysis, finds 51 neutrinos in the direction of NGC 1067, with this flux that is relatively soft. So the flux is about e⁻³ and another interesting thing in this observation is that the neutrino flux is overwhelmingly higher than the gamma ray flux observed by Fermi and Magic, and which suggests that obscuring should be happening inside the source, and the gamma rays that are produced at the same time in the pion decays with the neutrinos should be absorbed and not arrive at us. So in this context, I'm going to talk about the high energy neutrino from the Coronal AGN, which can explain the high energy emission from secret galaxies like NGC 1068. So an intriguing and puzzling thing that I mentioned in the spectrum of high energy neutrinos is the higher level of flux at lower energy, which is usually referred to as medium energy excess. So here you can see the different fits to the IceCube flux. In addition to the muons and the high energy starting event that I was originally showing, I'm also showing the Cascade analysis 6 years that also finds a flux that is softer than the muon tracks, and it goes to lower energies than the track analysis. And the magnitude of the flux, as I mentioned, is higher than the one above 100 TeV, almost an order of magnitude, which if you consider the multi-messenger interface and the connection, the gamma rays that are produced alongside the neutrinos in the sources that are responsible for this excess have to be absorbed and cascade down and should not get out of the source. Otherwise, they would violate the isotropic gamma ray background that we have seen by Fermi. So if the sources of these neutrinos are extragalactic, their origin should be obscured to GeV gamma rays, and they should not leave the source. So the agent, this Corona model can actually provide such scenario. The cores of active galactic nuclei, which are optically thick for GeV to TeV gamma rays, are one of the best scenarios to describe the medium energy excess. And the presence of the corona has been established in Seyfert galaxies with high magnetic field, hot and turbulent region around the core, and it's highly magnetized. And it can, as I mentioned, it has been shown that it can successfully describe the level of the neutrino flux that we have in the range of 10 to 100 TeV. And the gamma rays that are produced, since the core is thick, do not survive and cascade down, which will appear at MEV energies. We don't have a telescope running at these energies, but it means that they are not going to contribute to the isotropic gamma ray background, so the model is safe in violating this path. So let's have a look at the magnetized corona model. As I mentioned, the corona is about the core is thick and it's hot and it's magnetized and it's turbulent, and it provides acceleration of ions via either a stochastic and or magnetic reconnection. For the stochastic scenario, we solve the diffusion equation. Our cosmic ray injection function takes information from takes input from the intrinsic X-ray luminosity, and the size of the system and the injection energy basically defines the cosmic ray spectrum. And we consider the diffusion of the cosmic rays as a Kolmogorov of turbulence with the index of 5/3. And our input parameters here would be the pressure ratios of the cosmic rays to the thermal pressure and the strength of the turbulence inside the source. For the magnetic connection, we solve the transport equation. We inject cosmic rays with a simple power law, and we use the accretion rate that we deduce from the X-ray luminosity to find the level of the injection, and the cutoff in the spectrum is created by the interaction, acceleration, and the cooling processes that we have. The input parameters in this scenario for us is the energy fraction that is carried by the cosmic rays, which is equivalent to the pressure ratio that we have here, and the acceleration efficiency that we have. And for the cooling processes, we consider the PP, P gamma, and the beta Heitler processes to model the emission here. So when we adapt the parameters that can provide a compatible emission with NGC1068, as it has been seen with 10 years of IceCube observation, the intrinsic X-ray luminosity of the NGC1068 is 10 to the 43 ergs. And depending on how much of the pressure ratios between the cosmic rays and the thermal emission, we have different scenarios. So the first is the stochastic acceleration with high cosmic ray pressure, which can describe the flux around 10 TeV. The flux has a bumpy feature and it falls very fast, which is compatible with the soft flux that IceCube sees. Then we have a modest scenario with a smaller cosmic ray pressure, which this combination is the one that can describe the medium energy excess, as you've seen in the previous slide. And another scenario is the magnetic reconnection, which can describe the high energy part of the flux, but fails to provide a high level of flux at lower energies. We can see that this can yield the same, it can yield significance since it provides a flux at higher energies. But if the flux is established as what you see in IceCube, this scenario is going to be constrained trivial. So here's the likelihood for identifying NGC1068 from the fluxes that I presented in the previous slide. So as you can see, the events that you get for the stochastic with high cosmic ray pressure is going to be the largest, and you get quite an excess if you have the magnetic reconnection. Putting that in terms of the p-value and seeing how likely these are to be identified over the background, we can see that the stochastic with high cosmic ray pressure can be identified in a little more than 10 years of IceCube. The magnetic reconnection surpasses the 3 sigma, but it cannot get to 5 sigma even in 15 years, but it's still identifiable in IceCube. But if the flux is actually the modest scenario for the stochastic, the 15 years of IceCube and even 20 years is probably not enough to identify the neutrino emission. And remember that these p-values are local. These are not like accounting for the trials that we have. And as I said, the magnetic reconnection is viable at this moment, but if the flux is found to be constrained to have a soft slope, this can be easily ruled out. So using what we've seen for NGC1068, we'll look for the sources that are similar and can identify and test the model that we put forward. So we select the 10 brightest Seyfert galaxies based on the X-ray surveys. And here is the list that we have. You can see that NGC1068 is the 5th in this list, But note that most of these sources are in the southern sky. And we incorporate the extra luminosity intrinsic and the parameters that we adapted for NGC 1068 to see the prospect for observation of these sources. So this is the flux from the 9 other sources other than NGC 1068 that we can see here. Again, the stochastic with high pressure provides the largest flux, although it is shifted towards lower energies. And you have the magnetic reconnection and the modest scenario as well for all of these sources. Among these sources, there are famous sources like NGC 4945, NGC 1275, Sene, and Circumnus Galaxy. And when we look at the prospects, we find that the NGC 1068 actually appears at the brightest source in IceCube, given that it's in the northern sky and given that it's relatively close to us. The other sources cannot be identified at a significant level with IceCube alone, and that gets us to discuss the future neutrino telescopes. So here you can see the aggregated fluxes from the 10 sources that we see here. Depending on which scenario, it can describe somewhere between 2 to 10% of the total flux. And besides NGC 1068, as I said, most of them cannot be identified at a significant level, which means a stacking analysis would be a better thing to do for these sources. Stacking in IceCube can provide enough significance for the 2 optimistic scenarios. So the stochastic model with high cosmic pressure can be identified in less than 10 years of IceCube with about 5 sigma. The magnetic reconnection can be identified in more than 15 years at the level of 5 sigma, or can be rejected if it's not actually the scenario. But the modest scenario requires next generation of neutrino telescopes to be found or rejected at a significant level. So the next in line for the neutrino telescope is the KM3net in the Mediterranean, which with its eye on the southern sky with a better sensitivity than IceCube, it can provide enough significance to see the sources which majority of them are actually in the southern sky. And as you can see, with 3 years, you can have better than 5 sigma significance for the stochastic scenario for Sene, and Circumnus Galaxy could be identified at quite a significant level. The magnetic reconnection and the modest cosmic pressure scenario for the stochastic could be identified at some level, but not significant enough. But it still shows a promising scenario. One comment about Sene and jet activity. Among these sources, Sene and NGC 1275 are seen with high jet activity, which is not seen in the other sources. And there is a possibility that the X-ray emission could see some contribution from the jet. Although the features that we see in X-ray are basically challenging the one zone scenario and the fact that the X-rays are coming from the jet, but nevertheless, we checked if the flux that we're projecting from Sene is compatible with what we are seeing so far. And as you can see, the IceCube Cascade upper limit is still above the prediction that we have in all these scenarios. So the next generation of neutrino telescopes are required to test the modest scenario that we provided here, and depending on what angular uncertainty we have, you would have different power. So with good angular resolution, KM3net can test the modest scenario. And even if we remove Sene and NGC 1275, which are kind of ambiguous with regard to where the X-rays are coming from, there is still enough power to test this hypothesis. Then the next in line would be IceCube Gen 2, which has larger effective volume, and it can test all the scenarios that we consider here and exclude or confirm the neutrino emission from Sieverts galaxies. So here is the summary one. I'm going to stop for questions here. As mentioned earlier, we have the first signs of anisotropy in the cosmic neutrino flux after a decade of IceCube operation. IceCube has identified a signal toward NC1068 at the level of 2.9 sigma, which actually suggests that the gamma rays are suppressed at the source. And this Coronal model can accommodate the neutrino flux and the gamma ray emission that we see from NGC1068, and future neutrino telescopes can definitely confirm or reject this scenario. For the next, my final point about this is that the next generation of neutrino telescope should have enough angular uncertainty at lower energies in order to be testing these scenarios, which can give us more sources and identify a lot of properties of these kind of neutrino emission. Okay, I'll stop here for a few questions if anyone has them.
I think Marcus has a question.
Yeah, hi Ali, very nice. So you showed a couple of plots where you had time scales on the on the horizontal axis. So in terms for IceCube, are these total observation time, or is this additional years of observation?
It's total observation time.
I see. So in the case of your stochastic model, you are basically already, I mean, you would see it at the 5 sigma level already, right?
Yes, yes, but the analysis has not been done, right?
And if I may, one other question: if you do, I mean, these estimates are, I guess, based on your own simulation software. If you would simply take the best fit flux from NGC and run it through your software, how many extra years would you need to see it on a 5 sigma level?
This one.
So this
model, so for 1060, for the stochastic high pressure, you need somewhere between 10 and 11. For magnetic connection, you don't get to 5 sigma in 15 years, and the models you cannot identify.
But you also showed from the 10-year study this butterfly flux, right? Yeah. If you would take this as an input without any modeling. This one, yeah, if you take the yellow one there.
Okay, let me. I find a little better than 10 to the power minus 5 that I showed in here. So I think I found a little better than 10 to the power minus 5.
Mm-hmm.
So maybe by, so I think it's 10 to the power minus 5. I think I get something like at the higher end of 10 to the power minus 6. That's what I get.
So how many extra years do we need to have this at 5 sigma with IceCube?
Oh, with IceCube. If it's this flux.
Yeah.
Wow. I can't remember, but I think it may be 12. I think
12 years. Okay. Mm-hmm. Thank you.
I will check that and let you know. Fine.
Thanks.
I think Irene was first, and then Enrico.
Yes, thanks. I wanted actually is connected to what Marcus was asking. In this plot where you had the butterfly for the diffuse flux, and then the stochastic model is basically on top of the butterfly. If I understand this correctly, you were saying this is for 10 years of data. So this would mean that unless the flux changes within the next couple of years, then basically that part of the diffuse flux can be interpreted by using this NGC source.
And
not this plot, the other one where you had, it's like the yellow.
This one?
No, I think it was after, well, I don't know if it is before and afterwards, but it was, yeah, this one. So this is 10 years of IceCube, and then, yeah, the one that you were just showing.
This one?
No, yeah, this one. So this yellow band is for 10 years of data.
Yes.
And it basically is touching, is overlapping this red line that you have. So does this mean that if we wait for another 2 years and the diffuse flux doesn't change very much, then this high energy component of the band can be explained through the stochastic model?
So the medium energy would be, but this is a point source flux, right? This is not the diffuse one.
Okay.
Compared to the diffuse, this is what you get. So for the diffuse, you have this gap, right? It's higher for this one, right? So the thing is, if the stacking analysis of these 10 sources, like finds a signal and establishes any of these scenarios as potential mechanism for the production of the medium energies, then we can utilize it and incorporate more sources based on the X-ray surveys. And then that would definitely help us identify the origin of this region.
Okay, perfect. Thanks a lot.
And Enrico, and then John.
Hi, just a couple of curiosity on the NGC 1068 again. So I was wondering what is the dimension of this corona, and what are your assumptions in terms of magnetic field strength and coherence length?
So I don't have the exact numbers in mind to tell you, but the size of the corona here is determined by the X-ray luminosity. And so we use an analytic formula based on the model that Morasa and Kimura have for the corona model. So we consider the X-ray luminosity, find the mass, the effective mass of the black hole, and the bolorimetric luminosity, and we put that inside as the we use that as an input for the size of the corona. And it also depends on the acceleration size that we assume here. And so for the magnetic, I don't have the exact value in mind, but I can check for you.
Okay, if it is written in the paper, maybe I can find it there.
You have it in the paper.
And sorry, just another curiosity about this diffusion coefficient. Is there a typo in its energy dependence, or is not written in the standard way? Because e to the power 5/3 is not Kolmogorov. I would expect e to 1/3.
Why?
Well, 5/3 is the turbulence energy spectrum. Turbulence spectrum, not the energy dependence of the diffusion coefficient.
But there is a diffusion constant here, which is that dimension.
No, I think he means the energy dependence, right?
Yeah.
I don't think there's a typo here. I think it's 5/3 that we incorporate here. I think the diffusion coefficient here has a energy dependence here. It's not like the constant here is not dimensionless. That takes care of the.
Okay, so that is just the turbulence spectrum. Then there is another energy dependent function that is just fixed. Okay, thanks.
And then John.
Yes, thank you. So I had a naive question actually on slide 30.
13.
30. So it's when you apply basically your analysis of NGC 1060. Yeah, actually it was not 30. When you apply your analysis of NGC 1068 on other sources, so each time you have a number of parameters, and maybe so for this magnetic reconnection, stochastic component. And I was wondering, how do you fix it for these other gamma ray bright sources?
I see. Okay, so when I basically look at these fluxes, so the cosmic ray pressure and the the input parameters that I showed in the model slide that we were looking at when we were discussing the diffusion, we fixed those. So the parameters that we adapt for NGC 1068, we fix them. So the turbulence factor and the cosmic ray pressure is fixed for these sources. The thing that changes between these sources is the X-ray luminosity, the intrinsic X-ray. So between these and this source, the eta and the cosmic ray pressure is the same. What has changed is that X-ray, intrinsic X-ray flux or luminosity from these sources are different, and that creates the difference in the shape. For instance, this has greater than 10 to the 43 ergs per second, so you see it's sharply peaked, but for Sene, it's 10 to the 42 something, so it shifts towards lower energy. Another constraint that I didn't mention, but we consider here, is that we don't let the pressure to pass 0.5. More than 50% is not tolerated because it is not viable in this model.
Okay, thank you very much. Because I mean, because at the end of this analysis, you were kind of surprised that you find that NGC 1068 is the brightest sources. But if you calibrate the parameters so you calibrate the parameter, as you said, partly with the X-ray luminosity, but then we know that NGC is the brightest. It's among the brightest gamma ray sources. So no, I was trying to understand like this.
But the reason that NGC 1068 appears as the brightest is not because of its X-ray luminosity alone. There are sources with larger X-ray luminosity. The reason is that it's close by compared to the other ones, and besides that, it's in the northern hemisphere in IceCube analysis. So if Sene was in the northern sky, for which IceCube is the most sensitive to, it would have surpassed and become brighter, or even Circonus galaxy. But out of these 10 sources, 6 are or 7 are in the southern sky, which is a disadvantage for IceCube actually.
Okay, got it. Okay, thank you very much.
Okay, Ali, I think if I understand correctly, you still have some more slides, right?
Yes.
Okay, we're almost at the we're almost the 1 hour mark. So I suggest that maybe if you have like a couple of slides that you really want to show us, we do that, but no more than that. Would that be okay with you? Like a couple of money plots?
I can give the highlight of the 2 other topics very fast. If you give me a little more than 5 minutes.
I mean, yes. If people need to leave, please, of course, do so. But yeah, if you keep it to within like a few minutes, that would be perfect.
Okay, good.
So, thanks.
Thank you. Okay, another thing that I wanted to talk here, and Mauricio also mentioned in what was the galactic sources, and this is like my wishful thinking of the plane. We have all these beautiful wavelength observation of the galactic plane. I want to have this last one in neutrino. It might be like quite a dream for the current experiments, but eventually we should be able to see the galactic source of cosmic neutrinos, even if they are subdominant. So galactic sources can contribute to the flux. They are considered as the galactic component, although the isotropic distribution of the events means that they are subdominant. But we know that around the knee, the galactic cosmic rays are contributing to the cosmic ray flux, which should provide a neutrino flux by the interaction with the galactic environment. So we have done search for the major sources of the neutrino, the major source of high energy emission from the galaxy. Supernova remnants or unidentified sources, binaries, and pulsar nebula are among them. And it was based on the very high energy survey of the sky, which was first provided by Milagro. The expectation was to see sources after 5 years of observation of IceCube, but things got complicated when the tension arrives in the gamma ray observations. So our prediction was that more than 10 years of IceCube is needed to see sources, which one of them is Milagro J1908 plus 06, which has been seen with an excess in IceCube, but it doesn't reach enough significance to claim an evidence for neutrino emission. We used Hawk measurement to follow up on this. And what we find for 1908, I'm going to show that is that we are marginal to the expected neutrino flux that you can deduce from the Hawk observation. So the excess that we see is touching, so we're getting close. But remember, this is 8 years of observation. Additional years is needed to either constrain this flux or identify this source at the level of evidence. So we have 12 events with a p-value of 14%, which doesn't constitute evidence. But what this basically shows us is that we are getting close. Similar scenario is for pulsar nebulae. When you did a stacking analysis, our sensitivity is like marginal when it comes to the total flux that we see from all the pulsar nebulae. Although pulsar nebulae are not among like the ones that we would bet on because the leptonic scenario is most favored there, but we are getting there in order to be sensitive enough to do the searches. And we also looked at the binaries and we did a time-dependent search. And there with the episodic emission and the flaring point, we are seeing some sort of excess, but we are still not there. We don't have enough sensitivity. We need more years of data. We need joint analysis of upcoming detectors. But the main message here is that although it's probably less than 15%, the identification of galactic source of cosmic neutrino is likely with more years of data and future neutrino telescopes coming up, giving us better coverage. In addition, better techniques that are being developed in IceCube and other places are going to help us identify the origin of the galactic origin of cosmic neutrinos. I'm going to end with a very quick note on the high energy neutrino emission from the core collapse supernova. And this is something quite interesting. And I know that the NBIA has a particular interest in core collapse supernovae. So I'm going to very briefly talk about this. So the neutrino emission from the core collapse supernova constitute a rare thing that we can have multi-energy neutrino emission from a source. So the MEV thermal neutrino emission from supernovae has been established already by the observation of supernova 1987A. And it is one of the milestones in the astroparticle physics and neutrino physics, which determine a lot of unanswered questions about the collapse of massive stars. The growing evidence changed the picture for the supernova. The supernova remnants was one of the primary candidates for the acceleration of cosmic rays. But the expectation was that all supernova remnants, ages more than 1,000 years, are required to have enough density for the shock to be accelerating with the media to produce neutrinos. However, the picture changed when the extragalactic supernovae were observed in optical surveys. And there was an indication that the hydrogen line was observed. There was a significant mass loss rate in the very earliest stages. So somewhere between 0.1 to 10 days after the MEV burst, we now expect a flux of high energy neutrinos, which were, which for a source at 10 kiloparsec, it constitutes a very high level of time interrogated flux. So that put supernova type 2N and type 2P on the list of potential sources of cosmic neutrino flux. But it's a time-dependent analysis. Depending on how you define the analysis, you may or may not see it, and it highly depends on where the source is, because by distance you lose the sensitivity to site sources. What we did was we re-estimated the flux for supernova type 2P and consider this supernova type 2N also for current and future telescopes. And here is the updated flux from what you've seen. This is a work in progress. This should be out quite soon. But the previous estimate is showing a time integrated flux or fluence of around 5 times 10 to the 1. But the parameter that describes the mass loss rate based on the velocity and density, the wind velocity and density, has been underestimated. This is shown by the recent observation that the mass ejection is much larger than what has been estimated before, which basically can, for an optimistic scenario, can increase the level of flux by 2 orders of magnitude, which makes observation of supernova type 2P quite more likely. So putting it in a context of events that you would expect, for type 2N, since the flux is much large, given the distance, you may see at least one event up to 7 megaparsec. For type 2P, it depends on what parameters you input, but you can pass 2 megaparsec here. And what we show here is that the observation is plausible if we have future neutrino telescopes coming, including the ones in the northern hemisphere and IceCube Gen 2. So this is the probability of detecting multiplets. But what I want to show you here is mainly this. This is for the supernova type 2P, up to if that would happen in local galaxies. So not in the Milky Way, but the neighbor galaxies that we have up to 2 megaparsec. So the closest one, the LNC and SNC, can be seen in IceCube at level of 3 sigma. And the band here, it basically goes from the optimistic values for D star that I was showing at 1, or the pessimistic one that is 0.001. So you can see IceCube can find this, but as we have future detectors coming, we gain coverage to the northern hemisphere, which you can see with established SMC and LNC if they have a supernova type 2P as bit at a quite significant level. And then when we combine these detectors together, IceCube plus KMTNet and then IceCube plus KMTNet plus Baikal GVD, we can push this significance towards higher values. And as you can see, the horizon for identification at the level of 3 sigma can expand to more galaxies. And if we have IceCube Gen 2, we can actually have quite high significances here. And 10 to the power minus 11 here is a statistical kind of break that I put in the code, because for more than that, we don't have enough numerics to calculate this. So we basically, given that this was the smallest that we get, we put this floor for the p-value. So this is actually what we would expect. So we already know that a galactic supernovae can overwhelm with like 10 to the 7 or 10 to the 5 events that we would see in IceCube. But the thing is that nearby galaxies can also provide us a huge signal, which makes it very likely to be observed in IceCube and other future upcoming neutrino telescopes. And I should say that there's additional telescope that you can add here, basically balancing the sensitivity with Gen 2 in the northern hemisphere. The Pacific one can also be added in this list. And this is the final remark on this. The plot that I was showing before is assuming that the supernova is happening in each of these galaxies. It didn't include the rate of the supernova in the galaxy. If I include the rate in each galaxy and integrate it from here to 5 megaparsec, to basically taking into account the cumulative rate, the additions of the rate as I include more galaxies, the likelihood of observing at least one or two, basically doublet or triplet event in IceCube Gen 2 would grow, as we can see, by the additional years of observation. So if we consider 10 years of IceCube Gen 2 operation, with the optimistic scenario, we would definitely identify high energy neutrinos from the core collapse supernovae of supernova type 2P. Pessimistic scenarios would decrease this, but at the level of 40%, we are likely to see high energy emission from from core collapse supernovae. This is quite an interesting thing because it can actually help us establish a real-time analysis of an observation of cosmic ray acceleration, which can be very rewarding. Okay, I will skip the summary on the supernova part, and this is the summary for the whole file. The main message here was that we have seen the observation of cosmic neutrino flux now has reached its 10-year, it's near 10-year anniversary. We have IceCube running for more than 10 years, completely take for about 10 years. And we are eventually seeing some hints in the data that can tell us where cosmic neutrinos are coming from, what sources might be producing them. And given the progress in development of the new detectors, additions of the detectors, and the network of the detectors that are going to be coming alive, we have a high chance of identifying potential sources of cosmic neutrinos. I talked about 3 prospective sources. There are more there. This was not an exhaustive list. Tidal disruption events, anything correlated with gravitational waves, geodesics, and everything are still in the game and are quite important in understanding the high energy part of astrophysics. Thank you.
Thank you very much, Ali. This was super interesting, and I'm sure not only for me, but for more people. There were many questions already, so if there's one urgent question, we can ask it. Otherwise, we can always ask by email. I don't see any hands raised at the moment, so I'm assuming that anybody that's interested will contact Ali directly. But this is not for lack of interest. Actually, your last results are super interesting, and I'm sure I would like to have a conversation myself. So thank you very much, Ali.
Yeah. I would be happy to discuss any of this either online or offline with anyone if you're interested.
Thank you. And thanks everybody, and see you in a couple of weeks.
Thank you, Ali. Bye.
Bye. Talk to you soon. Bye-bye.